have a favorite, and it's obviously me.
That is.
It's
Doesn't every
me
teacher
because
have a
I'm the
favorite?
funny one in the class. Well, not really.
No,
but
you're
still.
not.
Guys, I
I'm
started
the better
recording. Can we?
Gracie,
Okay.
Gracie, can you calm down?
Can we focus now? I started recording, guys. So
You
don't have my
we're gonna actually start class now. Thank you. Okay, so we left off. We already got the vocabulary words. If you don't have those, they're on the video from yesterday, or I can give them to you at the end of class. So what we're gonna do next is move on to actually working some problems. So the first one should be in your interactive notebook already. This graph shows Liz's trip to and from Mount Hood. Find the rate of Liz's trip to Mount Hood in miles per hour. So the first time what we're doing is, this is where she's at Mount Hood, right here up at the top. This is her home is at 0. So she starts at home. She drives to Mount Hood, does her driving, gets there, stays at Mount Hood for a few hours, I guess, and then drives back home. Okay, so does everybody see what the graph is telling us at least?
Yes.
Awesome.
It looks like my forehead.
So what we need to do is we need to figure out how fast she's driving on her way to Mount Hood. To do this, we start at 0, 0, and then we decide, okay, what distance does she actually drive? So we count up until we hit Mount Hood is here. So we're going to go counting up on the side all the way up to here. This is each of these little lines here is worth 10. So we've got 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, and 150. So she drives 150 miles. And then to figure out how long it takes her, we count how far we go to the right. So in this case, it's going to be here, which is 1, 2, 3 to the right. So we can count that up here too. Either way works just fine. So we know that she's going 150 miles in 3 hours. Now, the way we solve this is all we need to do is divide these to get a speed. So we can say she drives 150 miles in 3 hours. 150 miles divided by 3 hours is 50 miles per hour. So her speed on her trip to Mount Hood was 50 miles per hour. So what we did here is the change in distance, which is 150, the vertical change divided by the horizontal change. Now that's going to be really important. We're going to be talking about that vertical versus horizontal change quite a bit throughout this unit, so make sure you're paying attention to where you're getting these numbers from. Oh, I saw Carmen show up, and then I think Ryan here as well. Oh, but now Carmen's back again. Yeah, right. Okay, cool. So I'll give you guys a second to get this down in your notes, and then we're going to look at the part 2. Okay, so part 2 is asking us to find the rate of Liz's trip home from Mount Hood. So this time we're going to start here, and we're going to go to here. Now again, we want to start by calculating our vertical distance. So we're starting at 150, and we're going all the way down to 0, which means once again, our vertical distance is going to be 150. That is not a very straight up and down line, but close enough. So we're going to hit right here. So we've got 150 miles, and then we got to count how far to the right it takes us. That's our number of hours, as we can see along our x-axis. So 1, 2 and a half. So right here, we've got 11 and a half minus 9, or 2.5 hours. So we're going 150 miles in 2.5 hours. Now, in the last one, we went 150 miles in 3 hours. And to solve them, we divided. So we're going to do the same thing here as well. We have 150 miles divided by 2.5 hours, which gives us 60 miles over 1 hour, or 60 miles per hour. So she was driving slower on the way there than on the way back.
Are we filling in all the notes on this page and the second page?
Yes,
Why?
because we
Can't
gotta
just-
get all of our notes done.
Yeah, we could do half today and half tomorrow.
We could, but tomorrow we're gonna be practicing stuff.
Mm.
It's not gonna be too bad. Does anybody need more time on this page? Okay. So this is a really interesting problem. This is all about reading graphs. So we're going to get some extra practice in right here. This says that Tamira rode the Ferris wheel at the state fair. The Ferris wheel made 3 revolutions before stopping. So with a Ferris wheel, if you think about it, you start at the bottom, then you go up and around, and then back down, and then whoosh, and then up and around. And so she did that 3 times, which means 3 separate times she was at the bottom and 3 separate times she was at the top. So first of all, the graph that we can rule out right away is this one in the middle, right? This looks like a straight line. She went up, she stayed up, and then she went back down. But we know that that's not the case because she started at the bottom, went up to the top, came back down, went up to the top, came back down, went up to the top, and came back down.
It's A.
So
It's
our question
A.
is it going to be graph A or is it going to be graph C? What I want you guys to do is I want everybody to vote on which graph you think this is going to be. And the graphs are height on the y-axis. So the vertical is representing the height, and then the bottom at the x-axis, sorry, lots of words. The x-axis is representing time. So A or C? Seeing a lot of A's. Anybody think it's C? Sawyer says D. Good job, Sawyer. Managed to pick one impossible answer. All of the above. Okay, I see you guys are taking this one real serious. So in this case, there's a problem with A. What this says is at 0 minutes, she starts at the bottom. That's fine. And then at about, let's say what, maybe 2 minutes or something. We don't know. We don't have units down here. But at this point, she's gone, or she's still at the bottom. And then she starts to go up. But then all of a sudden right here, she starts to go backwards in time. So now you can see at like whatever 2 minutes is, she's at this height and at this height, and that's not possible. So this graph actually has a time travel issue. We're going forward in time, and then we rotate and go back in time, and then we go forward in time, then back in time. So this graph A is, this Ferris wheel is traveling through time. So it's going forward and then back and then forward and then back. So we can eliminate A. We already eliminated B because the Ferris wheel went up once and then apparently broke down, I guess is what happened there. It's an interesting story. And then graph C is the correct one. So what this shows us is that at point 0, she was at the lowest height. Then she went forward until she hit the top. Once she hit the top, she was going back down. Now, the Ferris wheel was going in a circle, but time was still going forward directly. So you got to be careful with the time one. So C is the correct answer on this problem here. In general, if you see a graph with time on the bottom that goes like this, somebody did something wrong. Not always, but the vast majority of the time. I don't know. I guess if you're analyzing Back to the Future, then maybe you can have a. Also, hi Dawn. How's it going?
No, you would be the one getting it wrong since you're the one who gave us that problem.
All right. Is everybody ready to move on to the next one?
Yes.
Okay. So we're going to skip this. Now we're going to talk about direct variation functions. So a function is a direct variation function if the graph is a straight line that goes through the origin. So we'll look at graphs, which is the origin is the point 0, 0. So if it's a graph like this, where it's just got a like x and a y axis, then that's here. If it's a full graph with like all 4 coordinate planes or all 4 quadrants, then that's the center right here. The table of a direct variation function has the same ratio of y to x for every ordered pair. And we'll talk about what that looks like in just a second too. And then the equation has the form y equals mx. So this is what we talked about yesterday, where m is the slope or rate of change of the function. So it's just a number times x. It can't be adding anything. You can't have extra stuff. Just any number can be positive, negative. It can be a fraction, but a number times x. So let's look at some tables. We want to know whether or not the table models direct variation. So this table you should have, I believe it's on your second page, so you can flip to the back for a second. Yeah, it should be the top one on your second page. So we've got a bunch of different points in here, and we'll talk about those in just a second. But 0, 0 is a point in the table. We have 0, we have x equals 0, y equals 0. You can't do 0 divided by 0. That doesn't work. So we just leave this little line in here. I don't know if it's written in for you guys or not. It is. Okay. So you shouldn't have to write anything there. So since 0, 0 is in the table, so far we've checked off at least one box, right? It's gone through our origin, so that one's good. Now what we want to do is for all the other points, we want to calculate the ratio of y to x. So what is y in our first one? In our first point, what is y?
2.
Yes. And what is x?
1.
1. So our ratio is 2 to 1. Boom, right like that. So what I want you guys to do is try to calculate the ratios of the rest of these. And tell me if they are the same as 2 to 1 or not. So I'll give you guys just a couple seconds to try that on your own. So for each one, we're going to take the y value, divide it by the x, take the y, divide it by the x. And then just tell me yes or no, do you get the same thing for all of your points? Okay, I've only got one answer so far. Two answers so far. Okay. Addie, are you and Janie both in a car? Okay. Okay, so let's just move on to the next one. What is the y value for this one?
4.
Yep. And what is the x?
2.
2. So 4 divided by 2, we can reduce this down to 2 over 1. I think it's going to actually.
I had to leave for a little bit. I don't really know what's happening because my dog got into our cat food. So.
Okay, well then pay attention, Gracie, because we're going over some new things. So this table's on the second page of your interactive notebook, so you can flip back there. So what is the y value for this point right here?
6 to 3.
6 over 3, and 6 over 3 reduces to 2 over 1. And then last but not least, we've got 8 over 4, which also reduces to 2 over 1. So all of these points, all of the ordered pairs that they're giving us have the same ratio of 2 to 1. So the ratio is 2 to 1 for all points. So yes, this table does model direct variation. We've got the point 0, 0. That's really important. And then each of our points that isn't 0, 0 has the same ratio. So if we kept this going, up top, we would also have a point -1, -2. And if we wrote that out as y over x, we'd have -2 over -1. Negatives cancel out here, and we're left with 2 over 1 again. And then you could go so on and so forth in either direction. So this table does model direct variation. So make sure you've got all of these filled in. You should be able to do them pretty quick. And then we'll look at the next table in just a second.
Why do you make it look so easy?
because I have taught, I'm the teacher. I'm supposed to know math. You guys are supposed to learn math, which means you're supposed to make mistakes.
Okay, I finished the other table already.
You finished the other table? All right. So we want to know whether or not this table models direct variation. So Jasmine, you can just tell me yes or no. Do you think it does? But use private chat. So let's start. We've got 0, 0. That's a point on our table. So that's good. 1 check mark in our favor. Now we have to figure out the ratio of all of our other points. So somebody who isn't Jasmine, tell me, what is the y value for our first point? Guys, it's what's the y value for the first point?
It just kind of confuses me.
I know.
Okay, what is it,
Like-
Jasmine?
It's 1 over 1.
So 1 is our y, and then we divide that by our x, which is also 1. So what you're going to do is look for the value in this this y column, and then divide it by the value in the x column. So this one, we've got 1 over 1, which is just 1. This one, we've got 2 over 2, which can reduce to 1 over 1. But this next one, we've got a weird thing. We've got 4 over 3.
For 3, which you can't really reduce.
No, this does not equal 1 over 1. And then on the next one, we've got 5 over 4.
Which you cannot
So-
reduce.
We're calculating our y over x. We get all of these. So if you just look at the first 3 points, this looks like it's indirect variation. But then when you get to the bottom and you have the next 2, it is not going to work out. So the ratio is not the same for each ordered pair. So this table does not model direct variation. So when you get in a homework assignment, you might be given a table that has the values. Let's see. I don't have room to draw a table. Darn. Let's do it right here. It'll be small. So what if I had these values?
I know.
So in this little table that I drew, I know it's kind of hard to see because it's a little bit small, but
They
can
all
you guys
nine.
tell me, does this have direct variation?
If you multiply it, yes, but I no, it don't,
Why not, Jasmine?
because they're all random numbers that you can't divide it.
So that's not true because if we do 12 over 6, we get 2 over 1.
Okay, don't judge.
No, you're close though.
And 2 over 4 is 1.5, and same with 3 over 6, 5 over 10, 6 over 12. It's all 1.5. Well, 1/2.
You're doing it backwards, Tristan, but you're correct. They've all got a ratio of 2 to 1 for our y to x. But there's one thing that's different about this that makes it not direct variation. Does it have the point 0, 0?
No, don't.
No,
It has
it has the
0.
point 0, 1. So this is
Wait, does
actually
x go before y?
what? So you're doing y over x in the last column. So see how this is y divided by x.
Yeah.
So you put
Oh,
the
so
y
I thought
on
it was
top.
the same thing.
Yeah.
I thought it was the same thing. Okay, I got it.
So you put the y over the x. But the point was this didn't have 0, 0 in the chart that I drew. So that one doesn't have direct variation either. All right, let's move on. Let's look at some graphs. So what were our rules for graphs? We had, hold on, so many things to go back through. So a graph had to be a straight line and it has to go through the origin, the point 0, 0. So let's go back and look at these 3 graphs. So we've got graph A, graph B, and graph C. So which ones of these are straight lines?
A and B.
A and B, good. So we can immediately rule out C. It doesn't have a straight line, so that can't
I
be
think
direct
C.
variation.
I mean,
Okay,
like,
C, you think?
Yeah, see?
It's a straight line. C is obviously not a straight line. It's
If
curved.
C
up, very
is
bottom.
a straight. No, C is a straight line.
Well, if I was drawing the line and it looked like C, I'd probably be trying to draw a straight line, but for a computer, this is pretty not straight. So we can get rid of C right away. Now we want to look at which ones go through the origin. So does the graph of line A go through the origin?
Yes.
Yes, it
Yes.
does. So that means that A is a straight line and it goes through 0, 0. So this has direct variation. Does B go through the origin?
No.
No, it does
No.
not. So B is also not direct variation because it hits right here instead of down at the bottom.
C does
then-
though. C
What's that?
does.
C does
C
hit
does.
the origin, but it's not a straight line. So it's not going to be direct variation.
It's more or less like a half.
Yeah. So this is actually probably the right side of a graph of x squared. Or some form of it, which is super fun. But that's like algebra 2 stuff, so don't worry about that. So these are the three explanations for the graph. Graph A is direct variation. Another graph you could have in A that would be direct variation would look like this, except C. My straight lines are about as curvy as C, or like this. So it doesn't actually matter what the slope of the line is. As long as it's a straight line that goes through the origin, it has direct variation. And then no matter what the line is, if it doesn't go through the origin, it's not going to be direct variation. And if it's curved, it's not going to be direct variation. Okay, I think we've got 2 more things that we want to go through. And then we'll be done for today.
It's 3 more on my side.
Is it?
I got
Okay.
this weird table thing, and then I have y equals 3x, and then
Yeah.
another table.
Oh, yep, there is the small table. I forgot about that one. You're right. So let's look at the y equals 3x. This is back on the first page of your interactive notebook, so make sure you're in the right spot. So this one says, use the direct variation function y equals 3x. Now we know that this is going to be direct variation because we're not adding anything. There's no squared. We're not dividing by x or anything like that. It's just a number times x. So that's going to be direct variation. And we want to find the slope of the function. So the slope of the function when you're given a direct variation equation is the coefficient of the x variable. These are some big old fancy math terms. But basically, the x variable is just your letter x. Right? This is called a variable. Specifically, we're looking at the x variable because we've got 2. We've got the x and then we've got the y. So we're looking at the x. And then the coefficient is whatever number is being multiplied by it. So in this case, it's 3. So here, y equals 3x. This is the coefficient because it's the number that's in front of our x. So the slope equals 3. Easy as that. So what I want you guys to do is tell me what is the slope of y equals 4x?
4.
4.
Yep, 4. What about y equals 1/2x?
1/2.
Half.
1/2. 1/2.
Yep. Y equals negative 7x.
Negative 7.
Yep. Good job. All right, you guys got it figured out. So it's just whatever number is in front of the x is your slope.
Or fraction.
Or fraction. Or negative number. Doesn't
Or
really matter.
decimal.
Or decimal.
Or
Yeah.
decimal, yep. You could have y
Or
equals
centimeter.
0.5x. That works. It can't be centimeters. That doesn't work. Because those
Centimeter
are units.
isn't a number, it's a distance.
Yeah, it's a unit, so it wouldn't work. Okay. Hopefully you guys have that written down. You just have to write one number, so it shouldn't be too terribly hard. Okay. So next up, this is a little bit more complicated. Here, we've got a table. You guys should have this also right next to your y equals 3. Okay, it's on the same page. You should all know where this is. This table shows ordered pairs which model direct variation. We want to write an equation relating their x and their y coordinates. So since we know that this is direct variation, we know it's going to be y equals some number times x. So we want to figure out what the number is. Now, one of the ways we can do this is we can try to solve it using some numbers. So let's call our number, the number that we're going to multiply x by, we're going to call it n for right now. So we want to figure out what m is. Now, we've got some points in here that we can use. So we've got y equals 1, and when y equals 1, we know x equals 2. So what we can do is substitute those in. We have 1 equals m times 2. So what number times 2 equals 1? Can anybody tell me?
2, 1, 2, no, 2 or 1.
Nope. It's kind of both.
1/2.
1/2, yep. So our m needs to be 1/2. 1/2 times 2 would be 1. If we use 4 and 2, we could do 2 equals m times 4. 1/2 of 4 is 2. 1/2 of 6 is 3. 1/2 of 8 is 4. So we can find the slope by calculating the ratio y coordinate over x coordinate, and we can use any point. So in this case, 2 over 1, or sorry, whoops, y coordinate over x coordinate, 1 over 2, there we go. 2 over 4, 3 over 6, or 4 over 8. Any of those will work just fine. The only point you can't use is 0 over 0, and why can't you use 0 over 0?
Because
Enough.
it's 0.
Yeah, because it's 0.
Yeah, you can't divide by 0.
I was about to say it's not a number, but it is a number. It's just not. There's not really a value to use.
Yeah, so 0 divided by 0 is not a real number. It's undefined, doesn't exist, doesn't work. Funny enough, it can actually be a bunch of different things, but that's not really the point. That's calculus stuff. So in this case, we have y over x equals 1 over 2. So now we can write our equation in the form of y equals mx, which is just 1, or y equals 1/2 of x. So our final equation should look like this. Y equals 1/2 x. So I'm only going to give you 2 points this time. Y, x. Oh, I guess they did x, y, so I'll do the same thing. So let's see. Can you guys tell me what the equation would be for this one? Let's do 2 and 4.
It would be y equals 2 over 4x.
Almost. You flipped your y and your x. So remember, it's y coordinate over x coordinate. So in this case, we have 4 is our y coordinate divided by our x coordinate, which is 2. 4 over 2, we can just make that a 2. So y equals 2x for this one. You'll get plenty of practice with that in the future. So if you're a little confused on it, that is okay. All right, are we ready to move on from this one?
Yes.
All right. So the last one, whoops, there's just a little weird hanging 2/3 over here. Ignore that. So this has to tell whether or not each equation is a direct variation equation. Explain your choice. If it is direct variation, identify the slope. So let's go back and look. What are our rules for something being a direct variation equation? Whew, that's really far back. So equations, remember, it has to be in the form of y equals mx, where m is the slope or rate of change of the function. So it has to be just y equals some number. It can be a fraction, it can be negative, whatever, times x. You can't be adding anything, you can't be dividing, you can't do anything extra with it. So let's go all the way forward. There we go. Okay. So let's look at the first one. First of all, is this in the form of y equals mx?
Yes.
Yes. So does this have direct variation?
Why
Yeah.
is there a little 2/3 thingy down there?
You'll see in a little. I didn't animate it right. That's my fault. So this is in the form of y equals mx. So this is a direct variation equation for A.
Yep.
What is the slope?
That one I have to think about.
-2.
Yep, -2. Remember, the
Oh,
slope is
yeah,
just the
you're
number
right.
you're multiplying by x. So yes, and the slope is -2.
The next one's no. And
The next
no.
one, well, why is it no, Tristan?
Because it's 5 over x, not 5x.
Good
And
job.
x, yeah, and then the slope would, that doesn't even matter at this point.
Right. We don't know what the slope is because this doesn't have a normal slope. So no, x is in the denominator. So because x is on the bottom of our fraction here, this is
And then
not direct variation.
C, no.
Hold on, Tristan. Hold on. I want to give other people a chance. Type your answers in chat on this one, Tristan, because I think you've got it down.
Fine.
And Addie, okay, cool. What's the slope? Jasmine, that's in everybody chat. Okay, so on number C, or letter C, number C, whatever. On letter C, we have y equals 4x minus 3. Can anybody tell me, is this a direct variation? Is it in the form of y
No.
equals mx?
No, it's not because the X is in the wrong spot. The X
So
needs to be in the back, not up in the front.
No, X is in the right spot. It's just they should have put the -3 right after that.
correct, very good, Jasmine. So because we're subtracting 3, this is not direct variation. It has a minus.
Still
3.
right. It was a no.
Yeah, it's still a no. But the x is fine. This you could have had, like, if we had y equals 4x, this would be perfectly fine. But when we add in that -3, that's what makes it not direct variation anymore.
Oh yeah.
What about D?
Yes.
Yes,
Yes.
it is. And what
Everything
is
is
the
in
slope?
the right spot. 2/3 is the
Two-thirds.
slope.
Yep. Yes, and the slope is 2/3.
No for E.
No for E.
Uh,
Because it
Why not?
exponents too on it.
I think that could be. No, I think it is. Oh,
So
dang.
it isn't. This exponent does make it different.
Well, I was gonna say, but to the power of, and because it, like, I was thinking that it could be.
So this is actually called exponential variation. It's different, but it is kind of similar.
And
So
no
it'll
to
still
F.
hit the origin. It'll still hit it 0, 0, but it's going to be a curved line.
No, F is no.
F is also no, and that's just because now our 2 is an exponent,
Yeah.
or our x is an exponent. Good job. Sounds like you guys got it down.
Yeah.
Okay. So these are all the notes for our interactive notebook. There is a pretty easy short assignment for today in MathSpace. There's also an IXL version if you'd rather do that. So you can do either the MathSpace task, which is called proportional relationships, or you can do the IXL, which is IXL K7. I don't remember the exact title of it. It's in the Google Classroom if you want to double check. The rules for IXL this term is if you do the IXL instead of the MathSpace, getting a 70 will get you a 3 on the assignment. Getting an 80 will get you a 4. So you still don't have to go all the way to 100, but 70 was a little too easy on a lot of them. So I'm
Let's just do 100.
But you can do 100 if you want to do 100. That's
100 is
fine.
easy. It's not that much harder.
With math, it makes you do 1 question per point after 90, so it's kind of a pain.
Yeah,
Um,
it's good with me.
But
I
all
like
right,
math.
so once you finish taking the notes for these, you guys are free to go. If you have
Bye.
questions or if you want help with the homework, please stick around. Emma, what do you got to say? Frogs shall take it over the what?
Creepy body.
Emma's reading some weird poetry. All right. See you
Okay,
later. Emma.
bye.
Okay, let me stop recording before we
Bye.